All right, welcome to the seventh oral session of NIPS. We are very lucky to have Dr. John Hopfield here to talk to us about the emergent dynamics of attractor networks. So take it away. Thank you very much. Join me in welcoming.
Thank you. I was very happy to be invited here to speak, not just to speak, but to speak as a Posner lecturer. I had known Ed Posner, of course, in days when we were both at Caltech, and he was such an enthusiast for the intersection between neurobiology and engineering applications of neural networks. I moved office a few months ago, and in doing so ran through my old files, throwing things away, and ran across a sheet which actually describes a little bit of Ed's influence. This is the part of the program of a seminar day at Caltech in the afternoon of, I think, 1985. You can see Ed's role in several places. You can see, first of all, he gave the introductory talk, trying to set the tone for the afternoon seminars. You can see he gave one of the technical talks. You can see that there's both biology and neural net engineering applications involved in this seminar day. And if you look down at the bottom, you can see an ECP typed out. Ed, that's Ed's initials. He not only designed the program, he even did the typing out of the program. So this is very much in his flavor, still trying to bring neurobiology and engineering neural nets together. Some basic themes of neural-based behavior. First of all computers are dynamical systems. They compute by going from state to state to state, and the evolution of their state over time is what actually carries out the computational process. You don't tend to think of digital machines as dynamical systems, as all their dynamics is really in a clock. But as you move toward neurobiology and don't have a clock, you are really faced with much more bringing the dynamical systems aspects of computing to the fore. Carver Mead spent probably 150, maybe 200 student years in trying to develop analog VLSI in the flavor of neurobiology. And the overarching lesson of all of that research was simple. If you can manage to use the analog physics properties of the circuits in the computational process, a little bit of hardware can be very effective. If you can't manage to use the device physics in the algorithm, you might as well, as Carver would have said, make digital stuff. Now, biology is extremely effective in its computational processes. You don't have to try to quantitate that in any particular way, but given the slowness of biological hardware, roughly speaking, a millisecond clock at best, and given the amount of hardware you have, biological hardware carries out extraordinary computations for the amount of hardware available. And that has got to be because there's some kind of good match that evolution has found between the algorithms that are chosen and how the hardware operates. Now, the thing you're trying to understand in the long run from neurobiology has to do with macroscopic things. Look, you teach a rat to press down a lever when the bell rings. But every time the bell or the buzzer rings, it sounds a little bit different. Where the rat is in the cage is different, and thus the sound coming to its ears is different. At the behavioral end, the rat may press down the lever with his teeth, his front paw, a hind paw, his nose. The way the lever is pressed down every time is different. And in between, the behavior of all the neurons is different. And yet you have a robust behavior from bell press to lever going down. And you'd very much like to understand that aspect of neurobiology somehow. You'd like to understand neurobiology rising above the details to the extent that you possibly can. Now, large physical systems of simple components often have collective properties, and when they do, it's very useful to write down mathematics which has to do with the collective properties and ignore the details of what goes on underneath. The most complete example of that you can think of is probably the laws of hydrodynamics. Hydrodynamics is really about many, many molecules colliding and obeying Newton's laws of motion. Yet the equations of hydrodynamics, by the time you write them down, don't even mention molecules, and yet are an accurate description of things so good that you can use them to design the lift on airplane wings. That's because the laws of hydrodynamics are somehow emergent, coming from all the details underneath. They are caused by all the details underneath, and yet they, when you understand them, seem to have almost a life of their own. And you'd like to understand whether there are aspects of neurobiology which can be understood in that same fashion, in terms of collective behaviors, in terms of emergent behaviors, and not having to go back to what every single neuron and synapse is doing to understand the behavior. There are places in neurobiology where you can begin to see things which seem to be corners of that. For example, in the rat, and undoubtedly in you too, although nobody has actually found them, there are cells which respond only when the head is in some particular direction. If the head is in some other direction, the cell won't respond. There's a nucleus of head direction cells which keeps track of head direction. There's a large number of cells, maybe 100,000 cells, whose individual responses can be described by just knowing the direction the head is pointing. So there's a collective coordinate, the real manifold on which there's a manifold of activities. There's the activity space which is 100,000 dimensional, and yet the activities which you actually have are on a low-dimensional manifold of that space. You could say that that's because you're getting sensory input which is on that manifold, but this manifold is more than that, because it also keeps track of the direction of the head when you close the eyes. And so it retains knowledge of what direction the head is pointed through feedback connections, even when you have no sensory input. So there's a biological example of a system where there does seem to be a collective coordinate. Now I'm going to try to develop a simple collective coordinate for computational purposes. I've always found it handy myself to have some kind of physical insight into a physical system which I can more or less empathize with. And so before I tell you about the collective coordinate in neurobiology, I'll point out to you that the same kind of collective coordinate existed in computer hardware in the mid-'80s, late '70s in the form of magnetic bubble memory. If you take a very thin film of magnetic garnet, the magnetization likes to be up or down. Short-range interactions, the spins like to be parallel. Long-range interactions, they want to be anti-parallel. And so there's no way you can make the system overall be happy. And the result is there's a domain structure, which you can see here. There are stripes of spin up and spin down. There's a very clever optical technique wherein you can see the magnetization optically. And you can see that the system goes into a pattern of magnetic stripes up and down. If you put on a magnetic field, you get reduced to the system where most of the spins are in one direction, but you have these little islands, these little bubbles of spins which are in the opposite direction, magnetic bubble domains. These bubble domains are stable. They have, they're as real as bubbles of air in a liquid are, and you can move the bubbles around with forces. And magnetic bubble domain memory succeeded in making bubbles you can see the bubbles being pushed along. The dark lines are electrodes through which currents are run, and producing magnetic field gradients, and you see the little light-colored bubbles being shuffled from place to place. You don't have to ask about what the individual spins are doing. You become interested in the system in bubble dynamics. And that's the kind of thing that I'm going to try to bring to the neural net computational things. And you can take a one or two dimension, you can make things which are like these bubble states in the magnetic film. You can take a one-dimensional or a two-dimensional array of neurons and contrive the connections of them in such a way that most of the neurons will like to be off, but a bubble of them would like to be on, and you can move that bubble around. That's the kind of thing which I'm going to produce. These bumps, as they're called in neurobiology, the system I am describing is of a bump attractor. These bumps can be moved by forces, just as magnetic bubbles and magnetic bubble memories can be moved by magnetic field gradients. And these bubbles can be moved around in magnetic bubble memory by forces which are weak compared to the forces which it took to create the bubbles. And that way the bubbles stay as entities while you simply shuffle them around. I'm going to try to do the same thing in neurobiology. I'm going to construct a system which, through feedback connections, has stable bubble kinds of states, stable bump kinds of states, and which are pushed around by the inputs. And that pushing it around by the inputs is what does the computation. All right. What system? The computational problem I'm going to try to describe has to do with the following. When I say a word, you rapidly recognize it. If I say it, you recognize it, but if you are a lip reader and can't hear, you will recognize the word by watching my mouth. I recognize the way a friend walks at a distance 50 yards away from me, I recognize the friend not by what their face looks like, but by the way they walk. And when you think about it, biology is just filled with patterns which evolve over time, and you deal with these patterns by recognizing patterns which are not snapshots, but patterns which evolve over time. And I'll call these patterns dynamical patterns to distinguish them from the snapshot kind of pattern. And the thing which makes dynamical patterns typically difficult is that they are normally generated not at some very fixed rhythm, but they have a variable cadence and duration. And you want to do pattern recognition in spite of that problem of variable cadence and duration. If you're a computer science type, you'll say, oh, that's easy, I'll use a hidden Markov model. And they don't do badly. They're not superb, but they don't do badly. But on the other hand, nobody ever accused biology of implementing a hidden Markov model. I'm going to pick the particular example of recognizing spoken words in speech. It's a problem which is very well characterized, has engineering significance, and it's easy also to get intuitions because you can use your own hearing to try to understand what the problem is or isn't. Here are a couple spectrograms of spoken words. Time is going horizontally. Vertically are 20 different filter banks. Each filter bank is evaluating the power in a particular filter band. The filter bands are distributed like the psychophysical Mel scale, which is approximately a logarithmic distribution. And so you have, in these 20 filter bands, the lowest filter bank is at about 250 hertz centered, and the highest one is centered around 5 kilohertz. But these, you can see that the
Three.
All right, the typical 3, not very loud, sorry. Can that be turned up slightly or not?
Three.
Gives you an idea of the differences between threes of different speakers. You can see from the spectrograms there's quite a different cadence between the two speakers, and also some differences in where what frequency bands are emphasized.
Three. 0.
And so you have the typical things that you want to distinguish between and the things that you want to lump into the same bin. Now, looking at these, you'll sort of say, well, that's an easy problem. I can see the difference. But first of all, you haven't seen anything but the cleanest examples I could spot. And second of all, in bringing your vision to it, you're bringing a huge system, a large part of your brain, which you don't know how to actually simulate anyway, to work on this problem. So it's a real cheat to say that the visual system can do it. Sure, the visual system can do it, but we have to figure out an engineering way to do it. The information present, I've already just described. Looking for my cursor here. And in the modeling which I'm going to do, I simply have sparsified this information somewhat. I've taken not only a system like this, which has if I look in primary auditory cortex, already in the cochlear nucleus, I'll find cells which respond to particular frequency bands. By the time I move on to primary auditory cortex, there's cells which seem to emphasize onsets and offsets. And so I've augmented this spectrogram, which is represented here, by 20 other lines, which are simply the time derivatives of this spectrogram. There's no further information. I'm simply making a sparsified representation available, a technical point only. Now, how might I make a neuron which responds to some particular part of 3? Supposing I pick this part of 3 and I want to make a neuron which is broadly tuned to this time of 3 and doesn't respond so well to this time or this time. Well, you'd say it's easy. At this particular time, the signal you want it to respond to is an analog vector. It's pointing in some direction in 20-dimensional space. If I make a weight vector which is parallel to that, and make what goes into the neuron the dot product of the signal and the weight vector, that neuron will respond more to this time than to other times when the signal is not parallel to the weight vector. So it's easy enough to make neurons which are responsive to some particular time. But of course, if I make a neuron which is responsible to the end of 3, that's because it sounds like E, but 0 has a sound like that, and near the beginning is 0. Just trying to get short time sections to respond right is maybe a step in the right direction, but it doesn't come anything near solving the problem. The problem is trying to integrate information over this entire spectrum so that the decision you make at the end of the word actually reflects something about the entire structure of the word. I'm going to do that with a simple neural network, which is the following sort. They're on the scale of 100 neurons, more or less, 100, 500, 50. It doesn't matter exactly the number, whatever is convenient for your particular problem. Conceptually, they are arranged in a line. These neurons get inputs from 2 sources. One is they get inputs from synaptic weights, linking their inputs to the activity of these signal lines, which represent the fundamental information and which change over time. They also get inputs from feedback connections within this network. These feedback connections within the network are actually going to dominate the dynamics. The neurons involved are very simple. They are rate-based neurons whose firing rate is a simple sigmoid of the input current. The action potentials are only implicit. I do not actually use spikes, but since I have a firing rate and I have synapses, I can use the firing rate and the implicit action potentials to calculate the currents from synapses which, if they really had an action potential coming through them, would have a current which lasted a couple of milliseconds and died away. You'll notice I am carefully avoiding writing down much mathematics. At a meeting like this, I've always viewed mathematics as something which should be done between consenting adults in private. So I'll try to explain everything as far as I can with pictures. So here's my program for trying to make a system which will recognize words independent of cadence and be selective about the particular words it recognizes. I'm going to make a one-dimensional network, which is a bump attractor about 100 neurons long. I'm going to initiate a bump at one end. I'm going to let speech come along into the system and say if a bump is moved to the other end, I recognize the word. Well, there are two parts of this program. The first is making a system whose feedback connections produce a movable bump. And that's very easy to do. There's a well-developed lore for understanding this. If I make a network, neuron number is along here, so this pattern here represents the synaptic connections of a one-dimensional line of neurons. Nearby neurons have synaptic connections which are excitatory. Distant neurons have connections which are inhibitory. There's a simple stripe pattern of the connection matrix. And this is enough to stabilize a bump of activity anywhere along it. The bump is stabilized by having excitatory connections which, like the bump here, and by having inhibitory connections which prevent other bumps from going elsewhere. So it's perfectly easy to make a bump attractor and to control pretty well what you have in that regard. And I've taken the bump attractor, which is very simple because what I'm describing doesn't really depend upon the shape of the bump. It just depends on the existence of the bump and the ability to move the bump around. The problem comes in trying to design that set of connections which is going to make the input signal come in, and if the bump starts at one end of the line, it's going to move the bump along to the other end of the line. And it will do so only if the correct word is said. That gets a little bit trickier. Here's the way I'm going to go about it. I've described already how to make a set of connections so that at this particular time, I could design a neuron which was more strongly driven by this signal than it is by this signal here or the signal over here. I could do that for any time. So I'll do that for 100 different times. And that way, I'll do that for 100 different times. And that way I will be able to say what the connections are in this entire matrix. And we'll just try out and see what happens. So here's what happens when the utterance, this particular network was designed for the spoken word 3.
Three.
And you can see with 3 less, the word actually started here and ended there. I initialized the bump at this end of the line, and you can see that the input from the signal lines smoothly moved the bump in time. So it moved from one end to the other. Now, why did that happen? It's not magic. There was a design principle behind this. If you go back to the magnetic bubble case, what moves the magnetic bubbles? What moves the magnetic bubbles is the fact that the magnetic field is a little bit bigger over here than over here, and if the bubble is in the right orientation, the bubble would rather energetically be sitting where the field is bigger. In that same fashion, I've organized the connections so that if I look at the input to the neurons as a function of neuron number and a function of time, time goes along here, input number goes along here. Speech started here, and the early parts of the speech, the neurons near the front of the line had strong input currents going to them. The latter part of speech, the neurons, the latter part of the line had strong inputs going to them. All these inputs are weak, but what's actually happening is the following. Effectively, the inputs make a terrain. And the bump gets trapped in a terrain. There's a valley in the bottom of the terrain, and if the valley moves along in time, the bump is dragged along, and that's what does the computation. This just shows you that suppose you take another speaker saying
3.
The voice is rather more draggy, the cadence is different. This is what the input looks like as a function of time. It's not as simple as the other one was, but you can see that if the bump started here, the bump would be dragged up along here, and would reach the other end of the line at the end of the word. That's not very helpful, is it? It's at this stage that I'm very happy I got rid of my PC. Probably a corrupted file. All right, I will wing it from here. What happens if I present some other word to the system rather than the word 3? What happens? 3 was just matched a template in such a way that I had this systematic dragging of a valley along, and the bump went from one end to the other because it followed the valley. If I use some other word like 0, the input as a function of time looks very different. There's still an input pattern as a function of time, and it looks blotchy and so on, but there's no channel leading from one end to the other. And as a result, when I say 0 to the system, which is designed to recognize 3, the input does not succeed in moving the bump from one end to the other. The reason I picked these two particular examples was that 3 and 0 both have a strong E sound in them. You recognize 3 in the long run. When you recognize 3, the neurons which were designed to respond to E are on. But there was an E in 0, a strong E in 0 very early on, and yet those neurons which should respond to E were quiet. And the reason is the inputs from the signal world are actually quite weak. The only way you can get a neuron to be turned on is by moving the bump along. And the only way you can move the bump along is if the neurons are about to turn on anyway. And so when the E part of 0 comes on, the bump is way down near one end of the line. The E part of 0 would trying to turn on some neurons which are a long way away, and they simply are biased off so hard that the signal basically gets ignored. And so the system operates not by the signal creating neural activity, but by the signal succeeding in moving the ongoing activity from place to place, and thus changing the activity pattern. The system operates in a very collective fashion. I'll illustrate. I make the system, and as the bump moves along, a particular neuron turns on for a while and then turns off during the computational process. Supposing I removed the signal input from that neuron and left the feedback connections active, what would happen? Well, first of all, the recognition process takes place anyway because the whole mode of operation of the system as a whole is really quite collective. But more interesting, perhaps, is the fact that even that neuron, which now has no signal going through it, has an activity pattern which is a function of time, which is very similar to the activity pattern it would have had if it had a signal going to it. And that's because the activity pattern is dominantly generated by the feedback connections. And when the bump moves by this neuron, it goes on for a while and then goes off when the bump moves away. In this regard, one is reminded of things like in primary visual cortex, there's a layer of cells called layer 4, which gets the dominant input, ascending input from the eyes. Now that's where the signal comes into primary visual cortex. You would think that that incoming signal should dominate the activity of that layer. However, that layer actually has more excitatory connections coming from feedback loops than it does coming from the feed-forward connections from the signal. In short, if you look at things like primary visual cortex, you'll find a very heavily fed-back system in which the sensory input is not the dominant input to neurons. I am happily, by failure of slides, to be prevented from actually telling you a real piece of mathematics, so I'll tell it to you only in words. I've been describing this bump motion, but I've been doing simulations of all kinds of neurons and saying that just noticing that this bump is moving. I used the bump to help me design things, but I've done the simulation on all the neurons. You can actually find a set of equations of motion for the bump, which you can solve without evaluating the responses of individual neurons. There's a set of equations of motion for the bump, which in some sense is analogous to the emergent equations of hydrodynamics, a set of equations which allows you to predict and to analyze and to use the behavior of the system without actually following all the neurons in detail. Yeah, without the look. And look, for those of you who are being deprived of the math and want a math fix, about 3 days ago I put up on ResearchGate the first draft of a paper which covers all this subject, and you can find all the math you actually want there. But I introduced my talk with the claim that computations are easy to implement in hardware or neurons when the algorithm explicitly exploits the available device physics. I can now give explicit substance to this statement. The problem of dynamical pattern recognition can be approximately solved by using hidden Markov models and implementing this algorithm on a general-purpose digital machine. There is no direct relationship between the low-level computer hardware dynamics of a digital machine and the hidden Markov algorithm. Indeed, the very absence of such a relationship is what makes general-purpose digital machines useful. In contrast, the collective equation, which I have not succeeded in writing down for you, which describes the motion of this variable in terms of the signal coming in without evaluating neural activities, that collective equation describes a different algorithm for solving dynamical pattern recognition, an algorithm whose basis involves solving a time-dependent differential equation. There's a one-to-one correspondence between the solution of the mathematical differential equation defining the algorithm and the behavior of the collective variables of a simple neural network. This algorithm, unlike HMM, can therefore be efficiently and robustly implemented by a small network of neurons. You can do other You can do much more than do dynamic pattern recognition with the idea of manipulating bump motions, manipulating collective coordinates. Let me just mention one minor step forward, which suddenly says there are many other things you could do, and that is the following. I described a bump of activity which goes along in one dimension as moved from here to here by a signal coming into it. But I can equally well make a network which has a bump of activity which moves along and then comes to a Y branch and either moves up or moves down. And so it either goes like that or goes like that. If I were talking in terms of word recognition, I might like to have the word wonderful and oneself, which share a first common syllable, have a common stem and then a split in the word recognition hardware. But you can also see that once you have an ability to make decisions on the basis of an input, you have a bump in one part of the system, putting inputs to another part of the system to control bump choices of motion, and suddenly you are in the realm of building computers based on bump motions. In neurobiology, the place where I would look most strongly for bump motions in a way which is rooted in the same kinds of things I've been talking to you about is in the hippocampus, where there are place cells, and if you plot things up appropriately, you can plot a neuron's activity in a plot where the activity is located at the place where the neuron is spatially tuned. And so you can see in this plot, as an animal moves around, what seems to be a bump of activity moving around in this display. Now, I've described this, and it's often described in neurobiology, as though place cells were something which was simply controlled by the input. But if I have an input which is repetitive and so that you can develop a spatial arena which is very much looking for banana and two repeating syllables. In the word recognition system, the na and then the second na would have exactly the same synaptic connections, and yet one neuron would be active, or a different neuron would be active, depending on where the na was in the word. In a similar fashion, you can look for the question as to whether place cells are actually examples of collective coordinates rather than just responding to sensory systems by using repeated patterns in a virtual reality environment, where a question of whether you're here or here or here involves following along in an environment and not just sensory signals. All right, probably time to wrap up. Robust emergent behaviors of large systems, whether physical or biological, are a consequence of the behaviors and interactions of the more microscopic elements making up the large systems. One of the biggest challenges to neuroscience is to understand the causal relationship between different levels. For example, how language acquisition is a consequence of the structure of a brain and the dynamical properties of the neurons and synapses. Multiple intermediate levels of emergence will undoubtedly be required. I have focused on one tractable example of emergence, namely the utility of thinking about the motions of a low-dimensional activity manifold, both to understand some aspects of neurobiology and as a tool for artificial neural network computation. I hope that Ed Posner would have been happy to see engineering and biology still under one umbrella. Thank you.
So we have some time for questions. Please approach the microphones to ask.
Hi, John. So you talked about how you can think about sensory inputs as forces in moving a bump along a kind of a trajectory in a manifold.
Yeah.
Sometimes you might also want to be able to reset that location of a bump in kind of absolute coordinates. Do you have some mechanism where you can kind of reset the location of the bump as well as push it along?
Yes. If I were to, there are multiple things which can move bumps. One is, of course, I could just delete a bump by strong something and insert it somewhere else. Second of all, bumps are movable by asymmetric synapses. Here I made a symmetric network so the bump was neutrally stable, but I make a bump so when there's no signal on it, drifts back to the origin. Or if I'm trying to recognize words, I would actually do it by making the bump attractor in a loop with a very fast forward over here from synapse asymmetry, and it'll drift back here so there's one stable point where the system will actually reinitialize itself. I wouldn't have to do it. So there are various ways of putting forces on the bumps. You don't have to rely on the signal inputs to do so.
And what's your thoughts on where you mentioned places in the brain that could do this? You think that there's evidence now that you can collect to show this?
Well, in the hippocampus, the experiment which I would love people to do, and I talk about it now to try to get somebody to do it. Supposing I'm in virtual reality, and one wall has got all kinds of decorations on it, the other goes ABC, ABC, ABC. I'll learn place cells. So I'll learn a place cell for here, I'll learn a place cell for here. And both of those place cells have B on this side, but on this wall they got different things. Now, having learned that, I now go back to virtual reality, and I turn off this wall. And now when I move through it, the question is whether the place cells will still respond ABC, ABC, so that the place cell which had B input there and the place cell which had over here, which had exactly the same input to them, will actually, one be active in one point and one in the other point. It will be a very strong demonstration of the idea of these moving bumps and keeping track of the bump through feedback activity.
Thanks.
So John, I wonder if you could say a few words about how you engineered the bump that recognized 3. Is there a learning algorithm that you used for the synapses, or did you hardwire it?
I used one particular 3 as a template. And one of the important things about my writing down the equation, which you couldn't see, which defines an algorithm, is that with that equation, and not having to solve all the neural dynamics, you have something which you ought to be able to develop a learning algorithm, because in order to get the system to work well, you need those connections to be developed on a database, not just taken from a template of one particular item. I didn't have the guts to try to develop a learning program. I could demonstrate this with a template, so I demonstrated it with the template. But it cries out for learning.
Okay, so in the, so it's a great talk, by the way. I don't know if I could have done that without my slides. You just described in the answer to the previous question that maybe the hippocampus could be doing something like you're describing with the bubble computation.
Yeah.
But word recognition presumably isn't just happening in the hippocampus. So I'm wondering if you envision, this being something that's implemented in sort of auditory cortex, or maybe it's a higher level thing that's integrating multiple brain regions, or how are you thinking of it?
I really am, there's nothing sacrosanct about the hippocampus, but the nice thing about the hippocampus is it gives you an existence theorem that you can easily construct in neurobiology, a network which has about the right properties. It's simply constructed out of a typical piece of old cortex. Presumably any piece of old cortex could be used in this kind of fashion, or at least many could. And so I use it as an existence theorem. I don't suggest that the dynamical pattern recognition audio is done in the hippocampus.
Okay, thanks.
Thanks. So if I understand correctly, one requirement of being able to recognize 3 is that you see all of the phonemes in sequence to be able to push the bump along from the beginning to the end. As you noted, there are some other ways to recognize 3 by doing dynamic time warping against a template or by using hidden Markov model. Those methods might be a little more robust to a case where the R was dropped or masked out by noise because the prefix and the suffix both say there ought to be an R there. And so you would be willing to forgive the fact that what was there didn't sound very much like an R, especially if there was no other good way to explain the word as a whole. And so what I'm curious about is the robustness of the system that you've described.
And in this case, it's a question of if the terrain is less than perfect, what will happen? And one of the things which I was not able to show you was that I have showed you the terrain for a case where 1 and 0 are spoken simultaneously by the same speaker, and yet 1 can be recognized. You can see the valley. The valley is degraded, but you can see the valley going up there, dragging the activity from one end to the other. So it doesn't rely on perfection.
Well, that's a case where you're getting extra input. I was worried about the fact that the system seems to be conjunctive. So if you're missing any one piece of the input, maybe the whole thing fails.
If you're missing one piece of the input, the bump will supposing I just cut the input off. The bump will be in a position and it'll stay there. If I don't have the input off for too long a time, when the input resumes, a valley will move the bump on further. So there is some forgiveness there. You don't have to just recognize, it's not a 1, 2, 3 recognition, and if 2 is missing, you can't get from 1 to 3. It bridges the gap more gracefully than that.
Just like the other side of that question, kind of, if there's stuff in between, so for instance, if I said think really hard, so there's sort of the word 3 in there with ink in between, would it recognize that? Or I guess you can maybe have like one of these attractors back towards the start to remove that hypothetically. But
Will you repeat again what I'm trying to?
Think really hard. 3.
The things which are badly time warped are no problem because basically if the valley starts up like this and then goes over like that, you just follow the valley more slowly. What bothers you is when you get signal corruption rather than simply warpage of the time axis.
Well, not corruption per se, but I mean just like you can imagine and then 30 seconds of other syllables, and then and I mean, that's not the word 3.
In constructing the system, there's a motion which is caused by the moving the bump by the signal. There's also a weak motion put in, a bias put in from asynaptic connection, so that if you don't have the sufficient driving force, you don't move the bump. So there's a threshold which you can put in for requiring a signal to be like what the signal which you expect to get the bump to move. And so there are various tuning parameters. Look, I have no idea how well this will work. It will not work perfectly. But at least it is, because there's an equation of motion behind it, there's a well-defined algorithm which is actually implementing.
So the point is, I guess, like, if we do want to have time warping, so we'd like to be able to recognize 3.
That one's no problem, yeah.
Yeah, like, could we also have silence in between, like, 3 or something like that? I mean, it seems like you might want something that also pushes the bump backwards when you have something that is
That's what I've done with putting a small bit of asymmetry in the connections, in the feedback connections. I can push the bump backward with those.
All right, thanks.
And so that puts a threshold, says you really have to have a driving force before you get somewhere. It's what keeps random noise from eventually saying I'm a 3.
Yeah, but it still wouldn't, I guess, distinguish between random noise and just like slow, like warping or slowing down the sequence.
Because you do want to distinguish between these, you cannot make it to stretch the time arbitrarily. It won't do it. And you set it that way in order that it kills random noise from being recognized as 3.
All right.
Thanks.
So let's thank the speaker again. Thank you very much.